Okay, welcome to lecture 15. Um, Today finally we will use whatever we learnt about path integrals in the last few lectures and apply it to the case of field theory. And properly speaking, now for the first time we are actually going to be doing quantum field theory. But as you'll see, this subject is just enormously complex and requires a lot of formalism. So the first few lectures of this course I spent on classical Lagrangians and their symmetries, and gauge symmetry in particular, and then many lectures on the path integral formalism and how it's motivated. And now finally we'll be able to put everything we've learned together, and we'll take the following, we'll propose the following problem. So consider a classical scalar field. Phi of t and x, and let's fix it at an initial time. So we choose phi of 0. So actually we are going to now choose the time. So time normally we have taken to go from 0 to capital T, but sometimes we like it to go from t0 to tn. This will be convenient. So time goes from t0 to tn, and we'll divide this into n steps. So the first point is that at t0, we'll choose the field to be a particular function, phi I of x, where I is for initial, and at tn, we'll choose the function to be phi f of x, and we are going to specify these two functions of space only. Okay, it's a little tricky to understand the analogy, but maybe you're seeing it. In the quantum mechanics case, the function was called x, and at t0 it took the value xi, just a number, and at tn it took the value xf. Now instead the field at t0 takes the functional form phi I of x. Okay, so fixed time, obviously the field can still depend on x, and it's arbitrary, but we are going to just imagine that we have fixed it. And same thing for phi f. Okay. And now we are going to define a quantity which in field theory looks very strange, but we have to do it to be a sort of starting point, as a starting point of our description. And soon from it we'll derive physical quantities like correlation functions, which, as you already know, describe scattering amplitudes in quantum field theory. But it will be a little bit of time before we get there. So right now we are going to define a quantity which again is an analog of the particle propagator. I won't give it any name. It's not something we really like in field theory. Probably we wouldn't have been motivated to. Okay, I take that back. There is a motivation to write such a quantity, but right now I don't want to go into it. I will at some point go into it. So we'll just define this to be the quantum mechanical transition amplitude, starting with the function phi I of x at time 0, ending with the function phi f of x at time, so again this is t0 and this is tn, and in between there's going to be the field theory Hamiltonian times the time interval, where the time interval is tn minus t0. It looks pretty standard. The new thing maybe is that the Hamiltonian is going to be the integral over space of the Hamiltonian density of the field and its conjugate momentum. And actually I'm going to not use 3, I'm going to use small d. So space will be d-dimensional, it's just to make it sufficiently general, and space-time will be capital D, which is small d plus 1, dimensional. And we are going to break space and time separately and consider time evolution as this quantity indicates. And later we'll see that something nice happens which puts the space and time back together in a nice way. Okay, so this is what I want to calculate. Now, if you followed my previous lectures, there's almost nothing to do except to calculate it in the same way, but I'll go through the steps. What are the steps? If you remember, the steps are to break this interval into n smaller intervals, and then at each of those intervals insert a complete set of states. Now the complete set in the case of the quantum mechanical problem we did earlier was a complete basis of position eigenstates. Now we'll have to have a complete basis of field eigenstates, which is again a strange thing, but formally it has a similar definition. So let's go through it. I don't think I almost need any words. I can just write the formulae and you'll see that I'm just following what we did before. The goal will be to re-express this u as a path integral. Okay, but the paths will be in field space. The field will start somewhere and end somewhere rather than the particle. So they are not physical paths, they are paths in the space of fields. Okay, what should we do? Well, okay, so before we get down to it, we'll need to define this quantity. Yes, one second. Just let me say, to clarify things, that as before, we are assuming that we already know canonical quantization, and therefore H is an operator, and these are states, and we'll be using operators and states, but at the end we'll get a quantity which looks like a path integral. Yes, what was the question?
So these ket phi,
Yes.
is it same as phi of x acting on 0?
Yeah,
or?
I'm just about to define it. So the ket phi satisfies that phi hat operator at x and 0 and t0 acting on phi I of x and t0 is equal to the function phi I of x times the state. So what you have to understand from this function is given. This is my boundary condition. I had said that I am considering that the function that this amplitude will be taken with the boundary condition that at the initial time the field variable takes the functional value phi I of x, and of course the same equation will hold if I is replaced by f everywhere. So in this ket, this is just a label of the ket. We always label eigenfunctions by their eigenvalues. Okay, and this is the actual eigenvalue. It's a function that I pre-decide that I'm going to impose at the beginning and end. Phi I at the beginning, phi f at the end. Yes.
The eigenvalue is a scalar field, right?
The eigenvalue is a function of only x, not of t. It's a particular function of space. You can call it a field, but it's a 3D field, not a 4D field. Yeah.
So the operator in that equation,
Yes.
that's at time t0 or tn or?
Yes, yes. So this should be t0 for I. Okay, I was trying to be lazy. This equation is true with I, and the same equation is true with t0 being replaced by tn and I being replaced by f. So at tn, the operator phi at x of x at tn on phi f of x tn will give me the eigenvalue phi f of x. This is, so these are just the definition of field eigenstates. It's a little strange to get used to field eigenstates because I guess we don't really know any classical field eigenstates for scalar fields, but we do know for vector fields, I think. For example, if I say that in my lab I have a certain electric field, what I mean by that, classically I just have some electric field E of x at a particular time. But quantum mechanically, I mean that the electric field operator acting on the state that I've prepared gives me that electric field function back times the state. So a classical electromagnetic field is the one that we have good experience of classically. So in that case, you can certainly define a field eigenstate and you can also intuitively understand what it is. Okay, it will be the one where in the quantum theory the electric field is exactly what you want it to be in your lab. In practice, you don't make an exact field eigenstate, you make an approximate field eigenstate. So if some experimenter says they have made such an electric field or magnetic field in their lab, it doesn't mean they have made it with infinite precision. So, but it's very close to being exactly that. And that, in some sense, it's much like a particle, a position eigenstate for a particle. Nobody makes a particle that's exactly at a particular position, either in a lab. You can theoretically make such an object, but then, as you know, it will have an infinite uncertainty in momentum, and so you might think that you have made it here, but in fact, its momentum could be something crazy. So it could be whizzing around in a crazy way. So it's not a very practical thing, but approximately such eigenstates are natural, both position eigenstates and field eigenstates. Good. Okay. Now, what do we, very important question about these field eigenstates will be, as you can guess, we are going to insert them at time steps. But when we insert them, we must insert the thing which is called identity, and which makes use of completeness of these eigenstates. So with particles, that was the statement that we had the statement that the operator 1 is the integral of dx x x. At any time, this is true. With fields, it's a little bit more complicated. We still want to have an operator that's 1, but it has to be an integral over these field eigenstates I've defined here. Now this was at the initial time and there's something at the final time, but of course I can also define a field eigenstate at any intermediate time. Okay, so let me just consider the most general time. So it's phi a of x and time ta, and then the same thing in bra form. Now I should integrate it over something to get 1. So what should I integrate it over? In the case of a particle, I integrated over all possible positions. If the particle can go from minus to plus infinity, this integral was from minus to plus infinity. In this case, I want to integrate over all possible functions, phi a of x. Okay? And that's something strange. So I'll just give it a symbolic name, d phi a. But you must understand that this is supposed to be some symbolic integration over all functions phi. Okay, and that's exactly what we encountered in the path integral. The dx measure with a box bracket was exactly like that, except here it's supposed to be over functions on 3-dimensional space. Now, what boundary conditions should these functions on 3D space satisfy? Well, it's important to note that the 3D space is up to us. It's part of the specification of the problem. We are trying to quantize scalar fields. We can quantize them in a 3D space which is a box, or which is a Euclidean space R3, or which is a curved space, or which is a direct product of 3 circles, S1 cross S1 cross S1, that's called a torus. It's up to you. So we don't specify what it is. We say the 3D space is up to us, and the boundary conditions are also up to us. for example, if I'm quantizing fields in a box like this room, it's up to me to decide whether the fields vanish on the boundary of this box, or maybe the derivative vanishes on the boundary, or whatever I want. Okay, if I'm quantizing them in infinite space, then I would normally think that the fields fall off at infinity. But as I said, the choice is up to us. So we're not going to say more right now. Whatever this space is and whatever the boundary conditions are, this is assumed to be a measure which integrates over all functions satisfying those boundary conditions on that space. And it will be a matter of detail to find out what kind of functions are allowed given the space. Okay, the easiest space you can think of is if you make x 3 vector into a 1 vector. That's why I've taken the dimension to be d, small d. You could make d equals 1. Then we would be doing 1 plus 1 dimensional or 2 dimensional field theory. And then you could say, well, the space is just a circle. On a circle with periodic boundary conditions, it's very easy to find a complete basis of functions. In fact, we know what they are, right? They are these sine functions. They just return to themselves as I go around the circle. That simple. If I, however, take my 3D space to be R3, then it's a little bit more complicated. If I take it to be a 3-sphere, then it's some 3-dimensional analog of spherical harmonics. So as I said, what kind of functions we allow, what kind of space we allow, we simply bury it for now. And whatever it is, we assume there's a measure to integrate over it, such that this with this gives me the identity operator. Once we made that assumption, everything sort of follows trivially. And I almost feel I don't have to write the steps, but let's anyway do it. So notice that we are treating space and time very asymmetrically. We have chosen what is the space. We have also chosen what is the time, and the time is an interval. Okay, and the space is whatever we have chosen. And now this, we are going to insert 1 at every time step. T equals T0 plus capital T by n times at TA, which is capital T times A by n. So the ath step, the time is TA, and it's just T by n displacement from the original, and then we keep doing T by n times till we displace by T. Okay, so this is the time TA, and now we ask for the quantity this, and then so for propagation of this field from the b minus 1th to the bth step. And of course, first we write it by definition, then we manipulate that definition. So the definition is that it is phi b at x tb, and then now we have to actually put the Hamiltonian, and I'm going to make a standard sort of choice of Hamiltonian, which will be e to, and of course this step t by n will be called epsilon, as I did before. So small interval of time, and n is going to go to infinity, so it will be an infinitesimal interval of time, and I'm going to manipulate this ignoring terms of order epsilon squared.
So,
Yes.
I have a question in the previous, this completeness rule.
Yes.
So, when you say, so for position kets, when we have the completeness property, since we assumed it was R3, we could write x kets as whatever the vectors are in x.
Actually, we just assumed it was R because we were just doing a 1D
Oh, right,
particle.
1D.
Yes.
So,
Yes.
just all the x on a line.
Yes.
When we want to find out what the field space is,
Yes.
for that, you're saying that firstly you will have to know what like the x space is.
Yes.
Then you would have some boundary conditions on that.
Yes.
That will determine the field space.
Yes.
And then you write a completeness property in that field space.
Exactly right. And again, I made a brief reference, but let me just say that specifically, if my field space was the 2-sphere, then you know the spherical harmonics, right? And why do we write spherical harmonics? Because they are a basis of functions on the two spheres.
Right. So there the completeness relation would have all the this would be expanded as all the particular nth modes and
Exactly.
LM modes.
Exactly. So a generic function will be a linear combination of YLMs of. So the function will depend on, instead of depending on x1 and x2, which would be the coordinates of flat space, we'll switch to theta and phi, which are the coordinates on a sphere, and we'll write the function phi of theta and phi. Sorry, there are too many phi's in this problem. One is the angle, and it will expand it as some ALM, YLM of theta and phi. And then the measure over the functions is the same as the measure over just the coefficients ALMs.
Right.
So often we find the measure on a function space by finding a basis, and then the measure is nothing but the coefficient product of the coefficients.
Right.
Because if I vary over all coefficients, I get all functions. That's what the basis means.
So there, since it's labeled by a discrete index, it would be a summation over all.
Yes, and that's because the sphere is compact. On a compact space, and circle is a simpler case. The sine functions I referred to earlier are nothing but the YLMs restricted to a circle instead of a sphere, even easier. And it's always discrete when the space is compact, which means in practice that it's closed and bounded, doesn't go off to infinity. So we often do quantum field theory on such compact spaces when we are really not completely sure what we are doing. And then we can talk about taking limits of those spaces. So if your sphere becomes very large or your circle becomes very large, then effectively it becomes back to a continuous problem. So that's the way to think about it. Yes. Okay. So here we have to put, remember this is e to the minus I Hamiltonian times time interval. Time interval, this is one time step from TB minus 1 to TB. So the time interval is epsilon. The Hamiltonian is a field theory Hamiltonian. So it's actually an integral of the Hamiltonian density. And the Hamiltonian density is pi, for a scalar field, is pi squared by 2 plus half grad phi squared. Plus, let's assume we have a theory with a potential. So you can generalize this to theories with a lot of scalar fields, like an n component scalar field or a matrix valued scalar field. You can also in principle generalize it to a nonlinear sigma model, but not so simple. So we'll just do this. In any case, we are not doing anything terribly rigorous. We are just motivating a result. And once we are done with the motivation, we'll forget about this derivation, so-called derivation. Okay, so this is as much as this is for the infinitesimal amount of propagation from TB minus 1 to TB. The next step, as we've done before, is to break the exponential into two with an error. Oh, this is small d. This is the Hamiltonian is the integral over space of the Hamiltonian density. And this pi, I suppose you realize, is the field conjugate to the field. So it's phi dot in practice, but we call it pi, treat it as independent. And then I have e to the minus I epsilon, everything else. And then this. Okay, after this, the next step is to evaluate this, which is easy because it's acting on a field eigenstate, and phi hat here take the eigenvalue phi b minus 1. On the other hand, this is pi, so in here I need to introduce pi, a complete set of momentum eigenstates, exactly what we did in the particle case. Once we do that, this one evaluated on this pi will just give me the value of pi, pi of x. This is the functional, again, complete set of states. While on that side, I'll get the overlap of pi with phi, which will give me a plane wave analog, e to the I pi phi. And then this phi with this pi will also give me e to the I pi phi with a different sign. And so in the end, I will have integral t pi this is again the spatial measure, e to the minus I integral d dx. So now this pi squared by 2 is not an operator, it's a number. It's a function actually. Is the eigenvalue of the operator pi hat acting on a pi eigenfunction. Okay, so that's that. And there's always an epsilon outside every integral. Then here I get e to the minus I epsilon. That thing, you should stop me from writing capital D's. There should not be any capital D's in this discussion because we are doing everything at fixed time intervals. So here the operator phi has turned into phi b minus 1. However, as I did before, I'm going to pretend that phi b minus 1 is the same as phi b, and the error is again of order epsilon square. So from now on, the error just won't be written. Plus v of phi b. And then there was a pi here with this phi and another pi here with this phi. Everybody has been evaluated, all the operators have been evaluated. And so the function that I get now is e to the I, it's a third exponential, integral d dx. Pi phi b minus phi b minus 1. What you have to realize is everything here, pi and phi b minus 1 are all functions of space. So they have to be integrated. Okay, this is the field analog of p dot xb minus 1. Okay, I hope you can sort of see intuitively how this is like an infinite dimensional version of whatever we've done before. Okay, wherever we had, like when you say p dot x, there's a sum over, if it's three-dimensional, then it's p1 x1 plus p2 x2 plus p3 x3. The analog here is phi of x times phi b of x minus phi b minus 1 of x integrated over all x. So x is like the label. Okay, and now of course we see that there's an integral, there's a path integral over pi of a Gaussian times pi phi b minus 1, and I can do that integral by completing the square. Every time I do those integrals, I get some measure factor, and since I haven't exactly told you what this measure pi is, I can't know the measure factor. But by now you know that I'm never going to know the path integral measure factor, so I might as well not worry about it from the beginning. Okay, so continuing in this way, I finally end up. So the key step is that when I do the pi integration, I have to complete the square of pi squared and pi dot this. So I'll get this thing squared, but instead of having epsilon upstairs, it will end up having epsilon downstairs. And since this is phi b minus 1 divided by epsilon, it's going to be and is going to be squared. So this will be d phi by dt. That's how the time derivative is going to come. So let's write it. So from there, we come back here to e to the I epsilon integral d dx phi b minus 1 squared over 2 epsilon squared minus half grad phi b squared minus. Now the minuses I'm writing here are this minus, because it was e to the minus iht in the beginning, and then minus v of phi d. And yeah, there's one epsilon outside everything. And up to here, I've consistently neglected terms of order epsilon squared, so they should be there. Now I will take the limit as epsilon goes to 0, and this will become e to the I epsilon d3x half phi dot squared, that's this term, minus half grad phi phi b, this is minus v, and this thing I'll just call it dt. Remember, I'm just evaluating one of the u factors in over an infinitesimal time interval. Yes. Sorry?
Small d instead of 3.
D. Yes. Thank you. Yeah. And as before, the miracle has taken place, and we've got the action. Phi dot squared minus grad phi squared assembles together to form half del mu phi del mu phi. Now this is really quite a miracle. We shouldn't celebrate just yet, because first we have to multiply and integrate and so on. So only what we found is that this thing has now become Lorentz invariant. That's good news. But now this thing should also become Lorentz invariant, and the measure that we integrate over should become Lorentz invariant. Then we can actually say that we have reached a Lorentz invariant description of QFT. So let's keep working. So we recognize this quantity as e to the I L dt. No integral over t, but L is the integral of the Lagrangian density over d dx. That's what that L means. If I now integrate over time, I will actually get the action. And so from this, assembling everything, I will conclude that the original quantity I wanted to calculate, u of phi n Tn e to the, semicolon phi 0 T0. Okay, I can't remember if I call this Ti and Tf or T0 and Tn, but doesn't matter much. Turns out to be the integral. Now comes an interesting thing. d phi b is the measure over functions at a fixed time tb over all of space, and I'm also supposed to multiply that measure over all the time steps b from 1 to n. And remember, I'm taking n to infinity. So this is going to make this thing also effectively continuous in time. Okay, and now this part is easy. Once I multiply all these together, this dt is just going to be summed, and we are going to get an integral over dt. So we get e to the I by h bar. Now I'm not sure where h bar went in my discussion. I have a feeling I set it to 1 long ago. So e to the I s of phi. And now s is actually integral of d capital dx, the Lagrangian density of phi and delta phi. Yes.
When we did this for the quantum mechanical path integral,
Yeah.
there was a dp integral that we completed the square root.
Yes. Same thing here.
So, but here, so there we left one measure with no sort, like we said we won't comment about it, but there would be a measure.
Measure. Yes.
Whereas here we have taken an integral and like, because we took an integral over the another unknown measure d, like d pi.
Yes.
And
Yes.
that was a version.
Correct.
So we kind of like assumed that it would be give the
Yeah.
same.
The slight difference is that here the measure d pi can be given a good definition if I'm on a compact space, because if I can give a definition to d phi, then I can give a definition to d pi, I think. Because phi, so, yeah, I mean, I don't know what else to say. I mean, yes, I haven't given you the definition of, oh, you're asking about the one that I already integrated out.
Yeah,
Yes.
because
So,
there we had
yeah.
a DP, which
Yes.
was well known.
DP is well known, but yeah, we just integrated out and assumed that we'll get a Gaussian, we'll get the standard answer of a Gaussian. We didn't actually care what the answer is. We simply completed the square and then said d pi e to the I pi times anything is a Gaussian, and we don't care what it is. It will depend on the phi's at the endpoints. We'll simply subsume all that into this final measure. So, or you can put a number out, you can put a normalization factor outside.
So like even if that is divergent, we
Yeah.
can factor it into this.
We factor it into this and we worry about this as a whole. Okay. Now there are three things to analyze. Okay, so the next step. Yes.
Sir, you are assuming the completeness relation, but here we do not deal with Hilbert space, right? It's Fock space, so how do we know?
Now, why is it Fock space? It's Hilbert space. Why is it not Hilbert space?
Sir, we take Fock space, right? Because phi can, like, particles are created, so
I mean, phi is a field, and we are quantizing in the original formulation of QFT. See, Fock space is a particular representation of the Hilbert space in terms of oscillators, but even if oscillators may not be a valid thing to use. For example, if the field is, it doesn't have a quadratic term or something, I might not. I mean, that oscillator, if it's an interacting field, I can't use oscillators unless I'm doing perturbation theory. But I always have a Hilbert space. Every quantum theory is associated to Hilbert space. The Hilbert space in field theory is more complicated and has some issues with infinite it's more infinite dimensional, if you like, because the field theory itself has infinitely many degrees of freedom at each time. So it's more complicated, but it's still a Hilbert space and still should have all the features like completeness and so on. That's not to say that it's simple to prove them or define them, but the features are expected to hold. This is the domain of a subject called axiomatic quantum field theory, which actually sets out the precise axioms of quantum field theory, but it does so usually in the operator language. Here we are assuming that that's all known to somebody and we only use the broadest features of it. Remember, again, we are not doing a derivation, we are really doing a motivation. Yes?
So, does the Gaussian integral also work for summation? Because you said that there can be discrete fields like, for the eigenvalues. Doesn't necessarily have to be a summation of it.
No, even if not discrete indices, so the eigen values could be labeled. So as we were discussing on a sphere, you can label your functions depend on theta and phi, but they are equivalently labeled by the coefficients of YLMs. But we are still integrating over those, not summing over them.
No, we are summing over like YLMs.
Yeah, that sum is straightforward. The important thing is that we are integrating over the values of ALM. If we want to get all functions, we must write them as ALM, YLM, sum over all and M, and also integrate over all ALMs. Then we can generate all functions. So the Gaussian integral is always an integral.
So,
Yes.
but phi field here need not be Hermitian, right?
No, I've taken a real scalar field. All this is being done with a real scalar field. Maybe I should have said so, but since that is my Hamiltonian, it should be clear.
But I suppose you will eventually generalize this to other fields.
Sure, we will,
So
but
it
we
is
haven't yet.
complex fields then.
It'll all work, but we haven't yet. No, so let's do one thing at a time. We will generalize it. Okay, now there are three things to unpack here. One is this, one is this, and one is this. So what are they? This is the Lagrangian density. This is the 4-dimensional, or in general capital D dimensional integral, and this is the measure over all paths in that capital D dimensional space. Okay, So if we want to think that this result is Lorentz invariant, then we have to ask about each of these three things that I've underlined. And the only one which is crystal clear is the Lagrangian. The Lagrangian is Lorentz invariant by construction. And we've got the Lagrangian just because of this. Now there are no more space and time derivatives separately, so you've got the Lagrangian, so that's done. What about d dx? Well, let's remind ourselves that it is integral d3x over a spatial volume and integral dt from t0 to tn. This is not Lorentz invariant in general, because first of all we haven't said what is v, and secondly this has endpoints. Okay, so what we can say only is that this will become Lorentz invariant, or we hope it becomes Lorentz invariant as a measure if the spatial volume corresponds to Rd, Euclidean, infinite Euclidean space, and let's say t0 goes to minus infinity and tn goes to plus infinity. In that case, this whole thing goes to a four-dimensional space-time, infinite. And it's only in that infinite space-time that you can really make Lorentz transformations and not change the boundary conditions. Otherwise, you can see that if this is really from t0 to tn, then when I make a Lorentz rotation, a boost between x and t, then the new t is not going to satisfy these boundary conditions. So we keep that in our mind as a provisional fact, that this thing is formally Lorentz invariant, but only if we really take everything to infinity, infinite volume limit of space and infinite time propagation. Okay, so we just keep it that way, and actually everything hinges on what are we going to use this formalism for, and we are going to use it for many different things. In some of those things it will be Lorentz invariant because for example, when we do accelerator experiments and we want to predict scattering cross sections, then we can take the time effectively to be very large, and we can take the space also effectively to be very large. So there it will be Lorentz invariant. But for example, when we want to do finite temperature field theory, then T is going to be imaginary and living on a circle. And then of course, if this is on a circle and that's on some volume V, again we have lost our Lorentz invariance. But we keep that in our minds. So we just keep space in our minds for the fact that this is intrinsically Lorentz invariant, but this measure will depend on us. It depends what question we are asking. Okay. Finally, this is the, of course, the elephant in the room, as they say. So we are going to rename this thing in the limit n goes to infinity as d phi inside a box. Since we didn't know what was, this was a measure over space, functions on space. This is a measure over functions of space over space time. At present, these functions are such that phi at x of x and ti is the given function phi I of x, and phi of x and tf is the given function phi f of x, and this is a measure over all functions of x and t satisfying this boundary condition along the t direction, starting in a given function, ending in another given function, and over space satisfying whatever boundary conditions we specified earlier, depending on whatever space we specified earlier. It's always simplest to think of space as being made up of some circles or spheres, because then the boundary conditions are trivial. It's just single valued on a sphere, you don't have a boundary, and because we know complete bases of functions on circles and spheres, we know the function space very well. So that's always a good thing to start with, but in the end we will want this large volume limit. Okay, so very conditionally this whole thing is Lorentz invariant. This is good, this may be good, this also may be good in the same limit. When we take Ti and Tf to far past and far future, this looks better. But of course, we are never going to give a proper definition of this quantity. We are simply going to assume it has some basic properties, and then we are going to only construct quantities where we divide one quantity depending on this measure by another one depending on the same measure, and hoping that all normalization factors drop out. Very much like in quantum mechanics, we took the ratio of different determinants. Here also we'll get determinants, we'll take ratios, and that's how we are going to make progress. The new thing is that we are going to be able to connect these with actual physical observations, and it's going to become more and more natural to not worry about the measure, because in any case nobody seriously wants to know this thing. Maybe I'm exaggerating, but this is not the thing we really want to know. The thing we really want to know is, well, fields create particles, particles scatter, or particles form bound states, or particles decay. All of those probabilities can be measured, and we want to calculate those. And we'll see that any of those things that we want to calculate will involve a procedure where you'll automatically normalize, and hopefully the measure has a good measure factor, normalization factor, has a good chance of dropping out. So in field theory, it's actually going to get better and better to not worry about the measure too much. Of course, I always tend to overstate these things. It can come back and bite you in many possible ways. Maybe I should give you one little preview. We studied a lot of symmetries in the beginning of this course, like ON and UN symmetries of classical Lagrangians. There are theories of fermions where the measure is invariant under, the Lagrangian is invariant under those symmetries. Okay, this is not a problem, it doesn't know about symmetries, but it will turn out impossible to choose a measure that respects that symmetry, and then that symmetry will be broken in nature. These are examples where the classical theory has a symmetry, but its quantum theory loses that symmetry, because for certain technical reasons the measure cannot be chosen to preserve that symmetry. So you see, we go very optimistically saying, well, if there's a UN symmetry the Lagrangian has, then I hope my measure also has that symmetry, and most of the time it works. But once in a while, for reasons that people understand, it doesn't work. So just to give you the idea, it's not completely trivial. We should never take the measure completely for granted. On the other hand, the good news is, if all we want to do is simple perturbation theory, most of the time we can take the measure for granted. So it's always a bit of give and take. Some things work well, some things work less well. Actually, the fact that the measure there isn't a measure invariant under certain symmetries is a very good fact. It actually predicts an experimental result. It's called an anomaly. I don't know if you have heard of quantum anomalies. Anomaly is when the measure doesn't preserve a certain symmetry, and because of that failure, you actually find processes in nature which you wouldn't have expected on the basis of symmetry. And so it actually the failure of the measure also predicts things correctly. So there are a lot of miracles going to happen as we study field theory in the path integral representation. Okay, so good. Yeah. Now there's one more little step which is almost obvious. What if we want the partition function of a field theory? We sort of already got the basic idea before. We simply go to the imaginary time formulation and we get the partition function. Yes.
So again, the quantum mechanical version, this amplitude had a physical meaning of a particle.
Yes.
Probability of a particle, at least amplitude.
Yes.
Here, I don't understand what the amplitude is, because if we wanted to find the what is the amplitude for it being at x and y, then you would do a y phi x in 0, right? Rather than so.
Yeah, no, here the amplitude is to go from a field eigenstate to another field eigenstate. Okay.
But that is in the classical sense.
No, in the quantum sense, that is, you see, what is an eigenstate? An eigenstate of an operator is when the operator in a particular quantum state takes a classical value, a number value. So, to specify an eigenstate, I just have to give you that number. What is the eigenvalue that I want? So I assume that in the beginning of time, the field is put into an eigenstate of itself. That means it is in a particular field eigenstate whose eigenvalue is a particular configuration, and then at the final time the field eigenvalue is another particular configuration. So what you might ask is, where in the world do we actually produce field configurations like this? And the answer is that they are actually coherent states. So there's actually, even in ordinary quantum mechanics, the position eigenstate can be written as a coherent state, some operator acting on the vacuum, which satisfies. Well, it can be written in the language of coherent states. Or let me put it this way: instead of working in a basis of x and p in ordinary quantum mechanics, let's say harmonic oscillator, we can as well work in the basis of A and A dagger. And A and A dagger have eigenstates which are called coherent states, which are quite non-trivial. I don't know if you have encountered those anywhere.
It's in quantum optics.
Quantum optics, because they are very useful in quantum optics. Now with a field, you can also make a mode expansion of a field into oscillators, infinitely many, and you can make coherent states of those. Okay. Then those coherent states are things that you can consider to be physical in the language of a field. In fact, if, as he says, they learned coherent states in optics, it's because optics, which is the science of the electromagnetic field, has coherent states. So it's not as unphysical as I've almost been implying. A field eigenstate is something fairly sensible, but it's not the first thing that a particle physicist will think about, because they want to study what are called vacuum to vacuum transitions. So if I take Ti and Tf to be far past and far future, instead of saying I start with a field eigenstate, I'll say I'll start with the vacuum state, which is actually the best guess. What state is a particle in when it comes in from far away to interact in the LHC. We can sort of assume that somehow in the far past there was a vacuum state, some free particle was created over that, and then that came in unsmashed. And it's quite, once you take Ti and Tf to be far past and far future, it doesn't actually matter terribly much what state, what initial and final state you took, because it automatically gets projected onto the vacuum state.
So, like in terms of the electric magnetic fields, it's kind of understandable how this would arise. But if you measure a particle in a position state, is that the same as measuring a Dirac delta sort of field?
No, I don't think so. A particle in a particle in a position eigenstate is in a state where its position is a Dirac delta, as you say. The field is in a state where its entire function is a infinite dimensional Dirac delta. It's delta of phi of x minus phi I of x, product over all x. It's a horrible thing to write, but I'll write it. So in particles, we'll say that a position eigenstate at x0 in the x basis is delta 3 of x minus x0. This we understand, right? X hat on this gives me, in the x basis, x hat is just x, and since delta has the property that it has, these two are the same quantity. So I can say that x has the eigenvalue x0. So for a field, I have the field operator, and I make a delta not 3 but infinity. So this delta 3 is product of delta of x minus x0, y minus y0, and z minus z0, right? The analog for fields is that I have phi of x minus given function phi I of x, product over all x. With the usual...
Field space Dirac delta.
Yes. And it's product over all x. Like this is product over all space directions, I1 to being 1, 2, 3, this product over all x. So you will never stop, right? If you write this delta function as a product of factors, it will never end unless you're on a finite lattice. And you can practice by doing it on a finite lattice. So a field space delta function is that, for better or worse.
So you can't say that measuring a particle is like having a, say if it's a scalar particle, then it's like having the eigenvalue of a psi kept. Like that is not true.
So
Mm.
basically,
Hmm.
the eigenfunction is different than the operator acting on the vacuum state, right?
There's no vacuum state in this discussion. This is the field eigenstate, and it has the property then that when phi of x acts on it, the outcome is phi I of x, the known function acting on the same state. That's what it means to be a field eigenstate.
Right. What I was confusing this was like if you have phi x on vacuum state, then you would have like in the non-relativistic approximation it would be like the x scatter. Right.
Okay.
But this is different than
This
that.
is different from that.
Absolutely.
It's really the state which produces the state corresponding to a fixed function of space at a fixed time. The field is put into a definite function of space at a definite time. Okay, I'm out of time actually, so I'll stop here. It's very easy. What I was going to do is just to write trace of z equals trace of e to the minus beta h. Again, it's a good quantity we might want to calculate in field theory, though it often has some divergent features, but still it's a good thing to try. And of course, nobody will be surprised that it ends up being this, the integral over fields of e to the minus s in the Euclidean theory. It's the same manipulation, but again, this d phi has one extra integration compared to the previous d phi, because the previous one had fixed functions phi I and phi f. In this one, the initial and final functions are identified and integrated over. So, other than that, there's not much to say. You can talk about calculating it, but there's not too much to say about it. There is one little exercise. Let me write that and then end. From this, we can see that if you take the limit beta going to infinity of z of beta, then you get this, of course, as you know, is equal to schematically to the trace is always this, and this sum could be an integral. Now it's a sum or integral over all energy eigenfunctions of the full field theory. Okay, but now if I take this limit, then I simply get projected onto e to the minus beta E0, where E0 is the lowest eigenvalue of h hat, because this thing is equal to summation n e to the minus beta En. I simply evaluate h hat on n, I get En, and among all the terms in this, all the e's are larger than E0. So these exponents are damped compared to e to the minus beta E0 exponentially. So the only surviving term is this.
So the beta was tending to infinity, right? So what is e to the power minus beta?
It's the leading term in the limit.
But you have a beta in there.
Yes, I know. We write it like that. I'm sorry. That's how research is done. It's not a mathematical limit. The mathematical limit might be 0. By the way, I never said that E0 is negative or positive or 0. It depends on that. It could diverge if E0 is negative. It could vanish if E0 is positive, and it could be 1 if E0 is 0. But I'm not interested in that. I mean, this is shorthand in physics for the leading behavior for large beta, which means for low temperature, the leading low temperature behavior. And you'll have to get used to these kind of imprecisions. Physicists are not only not embarrassed by such expressions, but they are very proud of them. And you'll see them repeatedly in your career. Okay? Because it has a very genuine meaning. This says that this is literally this is 1 plus e to the minus beta E1 minus E0 plus ... You agree with that, right? I just factored out this from this. Now in the limit, I'm simply dropping everything that's small compared to 1. This is the leading term, so I can't drop it. If I drop it, I lose all information. But I take technically I'm taking so I can say limit of beta goes to infinity of e to the beta E0 times z of beta is 1. I mean, you can say 100 things, but whatever I said is okay. And so from this, it follows that E naught is equal to minus limit beta goes to infinity 1 by beta log z of beta. This, I believe, is an actual limit. So if I can use field path integral to compute z of beta, then I can take its log and I can divide by beta and I can take beta to infinity, and whatever number I end up with will be the ground state energy of my field theory. Now, I suppose in QFT1 you were taught that the ground state energy of field theories is typically divergent, but whatever that divergent expression, which is the sum over the vacuum fluctuations of all the modes, you will also get it by this method. So I have given that as an exercise. Yeah, any questions?
So
Yeah.
can we attribute all the divergence of the vacuum energy to the measure problem? Like the divergence of the measure itself.
I guess you can, because if there was no measure, you'd be in classical physics, where you just extremize the action and you're done, and then there's no divergence. So the measure is implicated in the divergences, but let's not go too far. You see, in quantum mechanics, there are no divergences, one particle mechanics, but we still had a problem with the measure. So the path integral measure is problematic no matter what. Okay, so we'll meet tomorrow to continue.